In this video, I'm going to go over the solutions from the second midterm in 2401 this semester. Hopefully this will provide some idea of, so help you figure out if you missed points, where you might have missed points, and make it so that in class we can discuss any problems people had with my description of the solution and how it works. If you find a problem with my grading of your solutions, where maybe you got some answers correct that I marked as wrong, feel free to let me know, or if you have any questions, additionally, please let me know either in class or at office hours, and we could talk about them. So there were 6 major questions, well, 6 groups of questions, 5 groups of questions, in this midterm. On this slide, I'm going to put, so here in the actual video, I'm going to show the approximate timestamp for when I start talking about the particular questions that were on the exam. So if you want to skip ahead to a specific question, you can use the timestamps that I've listed here. So these aren't in the same order that they were on the midterm. There were 2 questions on part 1 that I, in particular these 2 here, which I ended up throwing away for various reasons. So I left those to the end. So the first 4 questions or groups of questions are the ones that were graded, and then the last 2 are sort of a bonus, so you can see what the answer was supposed to be, and we can go from there. So let's get started. So the first question, and actually the first 3 questions, well, the first question was in 4 parts, and the question was based around this particular array, 3, -10, 5, 7, -1, 0, 7, 12, 2, and 1. And it said, given the following array of integers, what would the state of the array be after 2 passes of sorting using the following sorting methods? So here I'm saying 1 pass means that 1 element is placed into the right location. Here I say final location, but really I mean into a correct location. So the first one is insertion sort, and so here it's a little weird as to what I mean by 2 passes. So you can either, we know that an array of 1 element, right, is already sorted. So we could say the first pass places 3 in the right place, or the first pass is the one that places 10 in the right place. And actually the solution is set up in a way that it doesn't matter which one of those definitions you use. So like I said, the first, an array of just a single element is always sorted. So we start with element 1, which has the value 3, is already sorted. And remember, with insertion sort, what we're trying to do is we're looking at the first unsorted element and putting it into the right place in the array. So here we're trying to put -10 into the array of 3. So there's 2 possible places it could go. It could either go before the 3 or after the 3. And because it's less than 3, it goes before the 3. And now we're trying to insert 5. It can either go before the -10, between -10 and 3, and after 3. And since it's bigger than 3, it goes after 3. So this is the final result that I was looking for in the test. So notice that even if you had said the first pass was putting 3 into the array, the answer ends up being the same, right? -3 or -10, 3, 5, 7, -1. Right? Nothing else down here changes because we haven't gotten to processing them yet. All right. So the second part of it was looking at bubble sort. So here, bubble sort goes down and makes a pass by swapping elements if they're out of order as we go along the array. and at the end of a single pass, the last element has been placed correctly, right? So even if the maximum had been in the first element, it would have bubbled all the way through and ended up at the end. So with bubble sort, we don't automatically have the first thing in place correctly, right? We need to make a pass to get something there. So we start the pass at the beginning, we compare 3 and negative 10. They're out of order, so we bubble those two, right? So we're bubbling 3 up. And we move on to the next pair. We compare 3 and 5. 3 and 5 are already in the right order, so we don't have to do anything. Same thing with 5 and 7. And then we get to 7 and negative 1. So we need to bubble 7 past negative 1. So we swap these two. And then we compare 7 with 0. We swap those two again. Here we get to 7 and 7. So 7 is the same value as 7, so we can swap them. We don't have to, right? They're the same value, so it doesn't matter. We compare 7 and 12. They're already in the right order. 12 and 2 need to be swapped, and 12 and 1 need to be swapped. And now 12 is in its final position, right? So 12 is at the end, and it's already sorted. So the next pass is going to put the maximum here. The maximum here is 7, right? So it's going to put one of the 7s there. So it starts at the beginning. Negative 10 and 3 are already in the right order. 3 and 5 are in the right order. 5 and negative 1 need to swap. 5 and 0 need to swap. 5 and 7 are in the right order. 7 and 7 are in the right order. 2 and 7 need to swap, and 7 and 1 need to swap. And notice now 7 is in the right place. So this is the final answer I was looking for, right? Negative 10, 3, negative 1, 0, 5, 7, 2, 1, 7, and 12. All right. The next one is selection sort. So what selection sort does, remember, is it identifies each location and figures out what value needs to go there by finding the maximum in the unsorted values. Right? So it finds the maximum in the unsorted values and swaps it with whatever the value is here. Right? So initially we're trying to put the maximum value here in the last position. So we do a search across this array and we figure out that the max value is 12. So now we need to put 12 here at the end, which means 1 is going to go in the position where 12 is right now. Right? They're just going to swap. So now 12 is in the right place, and we need to figure out what needs to go in the second to last place. The second to last place is 7. So let's say we choose this 7 that needs to go in there, right? So this 7 is going to get swapped with the 2, and we're going to end up with this array. So we could have also chosen this 7. Depending on your implementation, you might choose one or the other. So both of these were the solutions I was looking for. Here, again, the only things that change are the 2, the position here 2 and 7, the position here with 2 and 7, the position here with 1 that got swapped with the 12, and then 7 and 12. I think some people implemented it where you put the positions at the front and you look for the minimum. In that case, this is the solution that it would have been. You would have found the 12, right? Or the negative 10 and swapped it with 3. And then you would have found the negative 1 and swapped it with 3. So that's why 3 ends up where the negative 1 was, negative 1 ends up where the negative 10 was, and negative 10 ends up at the beginning. So I think I counted all of the answers that did both. So all 3 of these answers, these 2, as well as this one, should have been counted as correct. Just because this is technically still selection sort, it's just not exactly the way we did it in class. So it's still valid. It's just not matching exactly the procedure we talked about. So then the final part of this question asked how many calls to merge sort would be made if the array above was to be sorted by merge sort. So we want to include the initial call. So the initial call is to this array, And remember, merge sort splits the array in half every time until we get down to arrays of size 1, right? Or ranges of size 1. And then it starts returning and merging those. So this is the first call, and it's going to make 2 calls to these 2 subarrays, right? Each of those is going to make 2 calls to these 4 subarrays, right? This guy is going to make a call to a subarray of size 2 and a subarray of size 1. This one makes 2 calls to subarrays of size 1. This one makes 2 calls. This one makes 2 calls. And now all of these ones where the subarray is only 1 element, we don't make any more recursive calls anymore. So it's just these 2 that end up being called again, and then we start merging up the tree, right? Merge these 2, we merge these 2. But this is the end of the recursion calling, right? These are all of the recursive calls that would have been made. So how many are there? Well, there's 1 call here, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 19. So the answer here was 19 calls to merge sort. Right? And they're exactly these subarrays here. And I don't know why I put -7 there. That's weird. Okay, so the answer to this was 19. So the next question asked us to explain the best case running time for insertion sort and give an example. So remember, insertion sort, given some partially subarray that's ordered, we're trying to figure out where the next element goes into that order. So the best case running time is O of n, and that's the case where it's already sorted, right? So if you try and examine where this goes into the array and it's already in the right place, we don't have to do anything. There's no work that needs to be done. All we do is compare with 1 element. So that's a constant amount of work comparing the yellow element to the last of the green elements and saying, yeah, this is bigger, so I'm going to keep going, right? So that means it's just checking and verifying, which is a constant time operation for each position, right? The next question was looking for the best case running time of selection sort. So remember, selection sort is going to look for the maximum value in the unsorted part of the array and put it in the right position. But that search for the maximum value takes linear time because it's not sorted, right? So we have to do a linear scan, which means each verification takes O of n. So the worst case, or the best case running time is n squared. And that's because no matter what, to determine the value at each position is in the right place, we have to do a full scan of the remaining numbers. So in this case, the worst case and the best case are the same, right? So selection sort is always n squared, right? The last question of this type was asking about merge sort. So merge sort, remember, we just went through this in the last question. It takes the array and splits it in half, and in half, and in half, until it reaches arrays of size 1, right? And it does that irrespective of the order of the initial input. So the best case, again, is the same as the worst case, which is n log n. So no matter what, the algorithm always makes 2 calls for any input larger than 1 item without considering their values, right? So it doesn't matter what their values are, it's always going to make those 2 recursive calls. And then merging, even if they're already in order, takes O of n time for each level because you're still going through and verifying, meaning the worst case and the best case time are the same at n log n. And that brings us to the final graded question from the midterm. Here we're taking a look at linked lists. So we want to perform a linear search on a linked list. So we've seen this on arrays many times, and we talked about linear search on linked lists in class as well. And this was a fill in the blank question. Again, some of the blanks might not be used. In this case, we need to put blank in the box, right? So let's remember what a linked list looks like and draw a little picture. So a linked list has a set of nodes that point to each other. The last one points to null. And we have one of those nodes as our head node, and we're keeping track of it, right? So if we're going to make a linear search through this, we need to be able to iterate through it. So how do we iterate through? Well, we first, on this first line, we make a new pointer called current, and that's going to start at the head node, right? Because we don't want to change our head node, otherwise we're going to lose all of our data. So we start at the head node, and then this while loop, right? The while loop here is going to be how we iterate through. So basically what we want to do is we're going to move current one spot each time until we get to null. So it stops when current reaches null. And to advance it, we say current equals current.next. So that's going to move it there, and then there, and then there, until we get to null. Right? Okay, so now we have our current pointer. We have our current pointer, and it moves along. But we need to figure out how to do the actual linear searching part, right? So we have an if-else statement. And we want to return true if the element is in our list and false if it's not, right? So the condition is going to be whether or not the value at our current node, right, val is our string, is equal to search. But is this the correct way to figure out if two strings have the same value? It's not. They're strings, right? So we need to use dot equals. So we say current dot value if it equals search, right? So if that's true, so ignore these semicolons that I put in on accident. But if the current value is equal to our search, then we're going to do something. Otherwise, we're going to do something else. So if it's equal to our search, that means we found what we're looking for, and we can just return true, right? But if current is not equal to our search, well, then we can just return false, right? So in this case, what if it's equal to this guy? Well, if it's equal to that, if we've already returned false, then we're never actually going to get there. So in fact, this blank needs to be left blank. We don't need to do anything there. We only return false if we get all the way through, right? We get to a point where we've reached the end of our list, where current is now pointing here, and we haven't found what we were looking for, right? Then we can return false. So there was an alternate correct solution here where this was left blank and this was current equals current dot next. Ooh. It looks much more readable on my iPad. Which is still valid because basically if this ends up being true, then we return. So it doesn't matter that we don't keep moving the pointer. And if it's not true, we need to keep going, which means we need to move this. So the reason we normally put this movement outside is that if we mess up the condition, then we can end up in an infinite loop, right? It would just keep looping without changing the pointer. But in this case, it's not ever going to happen because there's a return statement in here. So if it gets in here, it does the return, otherwise it moves the pointer. So this is also valid, and it was a correct solution. Okay, and then we're going to move on to the two synthesis questions where I was asking you to actually write some code. And both of these, they seemed like they came across as being more difficult than I think they needed to be. So very few people, if any, got this correct. So it wasn't really a good assessment of the topic. Remember, what I'm trying to do with tests is assess whether you know the material. And in this case, I'm thinking the question was not worded correctly. So I'm going to have to try again with a different question at some point, talking about binary search. So here we're going to assume that we have an array of integers that are sorted, but they're sorted such that all of the odd numbers are to the left of all of the even numbers. So within the odds and the evens, the numbers are sorted in increasing order. So an example of this could be 1, 3, 5, 2, 4, 6, right? So here, we're going to call this quote-unquote sorted, right? All of the odd numbers are to the left of all of the even numbers, and within the odds and the evens, they're in increasing order. So these numbers are still sorted in a predictable manner, which means that we can perform binary search. Right? So we want to write a method called binary search odd first list, which performs binary search on this list, which is sorted in this manner. So as is typical with binary search, we're given the array itself, we're given our search value, and we're given our range that we're looking for. So how do we tackle this? The way I would recommend breaking down this problem is to first, let's remember what binary search does. So let's ignore this whole odd and even thing for a second and just figure out how to write binary search as if it were just sorted in a normal order, right? So what's the first thing we need for binary search, right? For any recursive method is we need our base cases. So what are our base cases? Well, the first one is if the range doesn't contain anything. And the second one is if the range only contains one element, right? For binary search, for any recursion really that we're talking about ranges, we need to check that the range is valid, and we need to check that the range only contains one thing, right? Because we're looking at search. Well, if it's not a valid range, then obviously search can't be within the range, right? So we have to return false. And if it's one element, to know whether search exists in the range of one element, we just check if it's equal to that one element, right? Here we're talking about ints, so we can use equals equals. And we say, if the range is only one thing, then we're going to return true if it matches that one thing, if our search matches that one thing. And we're going to return false otherwise. Okay, so those are our base cases out of the way. And once we get down here, we now know that there's at least two things in our array range. There's at least two elements. So in that case, we need to perform our binary search. And remember, binary search says we're going to check whether the search element is in the middle. If it is the middle, then obviously we found it. Otherwise, if it's smaller, right? If it's to our left, we're going to search the left side. If it's to the right, we're going to search the right side. And we can know that it's on the left and the right because we know it's sorted, right? And we know its value in relation to that middle element. So the first thing we need to find is the middle index. The middle index is start plus n minus start over 2. There's a couple different ways of writing this, but this is the way I always write it. And then the first thing we check is if the element is that middle element. So if in array mid is equal to search, well, in that case, we found what we're looking for, and we can just return true, right? So we found it. We don't have to search anymore. We can stop. Otherwise, we know that it either has to be less than or greater than. It can't be equal to, right? Because if it was equal to, we would have done this. So if the search value is smaller than the midpoint, what does that mean? Well, if it's smaller than the midpoint, it means we have to search for it in the left half of the range, right? It must be. So if we have an array and we have our midpoint, if it's smaller, it has to be there. If it's larger, it has to be there. So this one is the smaller side. Smaller. And in that case, we just need to make a recursive call on this guy. So recursive call on binary search odd first. Does the array change? No, because we're given ranges. So the array doesn't change, the actual search value doesn't change, just the range changes. And in this case, if we're searching the left half, right, we're going to start at the same position, except we're only going to go to the middle, and we're going to exclude that middle value, so mid minus 1. And if it's not equal, right, it's not equal, and it's not greater than, it must be less than, which means we need to search the right half. Needs to be on that half. So we're going to make another recursive call, and here the end stays the same, right? But we only start at the middle point, but we want to start one to the right of the middle point. Okay, so this is all good, except, right? Except now we need to deal with this. The odd numbers are to the left of the even numbers. So we need to make a little bit of room. So these two really only come into play then if either the midpoint and the search value are both even or they're both odd, right? If one's even and one's odd, right? So if the midpoint is even and the search value is odd, what do we know? Well, we know that all of the odd numbers are to the left of the even numbers. So that means that if the search value exists, it must be in this part, right? And if it's the other way around, right, that this is odd and this is even, then we know that it must be in this bit if it exists. So let's add those two conditions, right? So if the midpoint is even and the search value is odd, so we know that odds, the search value has to be to the left of all the evens, which the mid value is, which means we need to make a call to the left side, right? Well, and similarly if one is even there, right? So let's go back to this guy. If the midpoint is even and the search value is odd, that means the search value has to be to the left, which means we need this one, right? And if it's the other way around, then we know we have to search to the right. Because remember, we already checked whether it's equal to, right? That didn't really depend on things. But we need to know which way to search, and that's based on odds and evens, and then based on their values within the same odd and even. Right? So if we look at this, the only thing that's different from standard binary search are these 4 lines. Right? So remember, we started with something we knew how to do, and we extended it to this weird sorting that we have. Right? So then the last problem was asking us to use recursion and write a method that finds the minimum positive number in an array. So assume that you always have at least one positive value in the array, and write this method. So here's our signature, and actually there was a mistake in the signature because I gave you an array of doubles, but I wanted you to return an int. So actually it should read that. Right? It should return a double. So how would I tackle this if I were to approach this problem? Well, let's think back to something we know how to do, right? The tricky part in this algorithm is probably the fact that we have to use recursion, which sort of makes it a pain, right? So let's start by writing a method to do this not using recursion, and then we can update it to be recursive. Right? But at least we can conceptualize the problem. So if we were to do this without recursion, what would we need to do? Well, let's have some double that we're going to keep track of. So this is our minimum positive number, and we're going to initialize it to -1 because we haven't seen any positive numbers yet. And then we're going to do some stuff, right? And then we're going to return whatever the minimum positive number that we've seen is. Right? And for now, let's just think of this as the minimum number. Like, make it even simpler. The minimum number in this range. So if we're going to do that without recursion, then we're going to need a loop. And we know that we have some range. So we have a start and an end. So we know we need a loop that goes from start and ends at end. And actually that should be less than or equal to. Right? Because end is an index. And then what we do is at each position, we check to see if the minimum positive that we've seen so far is smaller than the one we're looking at, smaller than the value we're looking at. If so, we're going to update our minimum. Right? For now, let's just call it a minimum. Well, we said it has to be only positive numbers, right? So we only want to do this if array I is positive. So that means if it's smaller than the minimum and it's greater than 0, right? Because this is the condition that it's positive, then update our array. There's one problem with that though, that's that we're starting at -1. So we need to, the first time we find a positive value, we need to make sure we set it as min pos. So we say, if we haven't seen any positive values yet, or this one is smaller, and it's positive, then we're going to update the minimum pos. So this is how we would do it without recursion. Right? We have some value that we're going to keep track of, and we're going to use some dummy value, -1, right? And if it's -1, we haven't seen any positives yet. If it's a positive number, then it's the minimum we've seen so far, and if we see something smaller that's positive, then we're going to update that. Well, what if we use the idea of ranges and say, well, what's the minimum positive number in this range? What's the minimum positive number in another range? And take the minimum of those two, right? So the first thing we need are our base cases. So again, we said when we're dealing with ranges, if the range doesn't contain anything, then we need to return a dummy value, right? That we weren't able to find anything. And if it only contains one element, right, then we can return that element. Well, why would this not work? Well, it wouldn't work because that element has to be positive for us to return it. So we need to say if there's only one element and it's greater than 0, return that element. Otherwise, return this dummy value because we haven't found it in this range. So we can assume that we have at least one positive value in the array, not necessarily in the range. Right? So then we can do sort of what we did before and break it in half and search the two halves independently. So we're going to find the midpoint, just like we did on the last problem. And we're going to make two recursive calls and say, what's the minimum positive value on the left side? And in order to do that, we're going to make a recursive call to find min pos using the same array. The array doesn't change, just the range. We're going to start at the same starting position. And this time we're going to go to the middle. But since we haven't done anything with the middle, we need the recursive call to do something with the middle. Right? And we're going to do the same thing with the right, passing the array, going to the end. And here we don't want to include the middle because we included it up here. So mid plus 1. Now we get these two values. They're either going to be, the options are a positive, it's positive, or 2, it's negative 1, right? And negative 1 is sort of our dummy value, which means there's no positive in this range. So if the left doesn't contain a positive, right? If we get negative 1 on the left, that means if there is a positive, it's going to be on the right. So we just return whatever that value is. The right might not have a positive either, but in either case, it returns a correct value. Similarly, if the right doesn't have any positive values, then if there's any positive values, they must be on the left, and we know what's held in left is the minimum positive in that subarray. And then the last case is if they're both positive, then we need to return the minimum of the two. So if the left is smaller, right, we know it's not negative 1. Neither one of these is now negative 1. They're both positive numbers. If the left is smaller, we're going to return the left. If the right is smaller, we're going to return the right. Right? So let's walk through an example of what this might look like. Let's say our array is negative 1, 3, negative 2, 5, right? Our initial call is to this, and then our next call would be to negative 1 and 3, and negative 2 and 5. It doesn't hit any of our base cases, so it's again going to make recursive calls to negative 1 and 3, negative 2, and 5. So this returns negative 1, this returns 5, this returns negative 1, this returns 5. So when we're looking at this side, well, left is negative 1, so it's going to return right, which means it's going to return 3. And again, left is negative 1 on this side. Left is negative 1, so it's going to return right, which means it returns 5. And now it gets to the point where left and right are both positive, so we're down here now. And 3 is smaller than 5, so it returns 3, which is exactly the correct value, right? The minimum positive. So the only positive numbers are 3 and 5, right? And 3 is the minimum of those two, which is the right answer. So hopefully that helps clear up those two questions at the end, and any other questions you might have. Again, if there were any discrepancies in grading, please let me know. If you have any questions about the The test problems, please also let me know. We might go over a little bit of this in class, but for the most part, we won't go over this until closer to midterm 3.